Let's wait like 5 minutes, no? All right. Yeah. I found it very expected. Yeah. All right. Let's start. Bueno, good morning. I see we have a lot of people, so having lots of equations and math yesterday didn't scare you away. So I will misuse this completely shamelessly and mistreat you to even more equations and maths than yesterday, a lot more. But hopefully there will be actually some simple conclusions at the end, which I hope will be satisfying. So we'll do kind of two chapters today that are very closely related. First, we'll talk about essentially the continuum problem of hyperbolic systems of partial differential equations, such as how we solve the Einstein equations in the time evolution for the time evolution problem. And in the second part, I will talk about how to discretize these systems and how to do this in a stable way, and what kind of theorems there are that tell you how to do things. In the numerical analysis of practical problems, it's really, essentially, there's a lot of black magic, okay? And sometimes you can get the impression that it's all black magic. But the point, if you want to do this well and successfully, you have to know some very basic mathematical theorems that give you a solid background of what's happening in principle. And then once you have understood this, and you have a lot of experience in doing simulations, then you can do some black magic. But there has to be a hard mathematical basis for this, otherwise you can get completely lost. All right? And so this is what we'll try to do today to give you like the basic results that are very important. Another remark, so I'll really focus on hyperbolic equations. As I said yesterday, the Einstein equations, they kind of split into two parts. Hyperbolic equations and elliptic equations, which describe the constraints. These elliptic equations, they're also very interesting to solve. In a certain way, you could even consider them to be harder, because elliptic equations, they are for boundary value problems, and you have to solve the whole problem at once. An elliptic equation, you cannot solve it just a little bit. Okay, you have to solve the whole problem at once. A hyperbolic evolution equation, in some sense, you can solve it a little bit, because it's a time evolution. You can make it just a short one. That should be easy. But the longer it goes, somehow the harder it gets, because errors can sum up and all kinds of things can happen. All right? But in the end, much more effort was spent to really do the evolution part right, and this is why I will really focus on that. There's a lot of interesting theory about elliptic equations. There were some controversies, some open questions, and so on. But I think it's a much more closed subject, and so I will not spend so much time on it. All right. So let's go. Let's start simple. Let's start with some. So we start with the continuum problem. Let's start with some simple questions to just get more feeling about the deep mathematical nature of partial differential equations. So the first question is: if you have a partial differential equations, do any solutions exist? Okay. And so a good way to start is to look at whether maybe at least analytic solutions exist. Okay. So consider, and so let's start simple. Let's start with a wave equation. We know very well the wave equation. So let's look at an initial value problem for the wave equation. And so here it is, our wonderful wave equation. You remember yesterday we had two formulations already for the Einstein equations. We had ADM equations, or York ADM equations, like usually call them, with the first ones that we had with extrinsic curvature and the 3 metric. There was another formulation which I called generalized harmonic, and I basically said if you choose this generalized harmonic H, that it's basically a nonlinear wave equation for each component of the metric. Okay, so and basically all this theory about well-posedness and so on, this goes with the principal part, and so it goes with for all of this theory. This is basically a wave equation with a lot of complications in the source terms. But for all these maths here, this doesn't give you much trouble. Okay, so essentially all the theory that we will understand for the wave equation carries over pretty well to the full Einstein equations, at least if you write them generalized harmonic. Okay, so that's why we spent a lot of time on the wave equation. So second order in time, second order in space, the Laplace operator. And so we can set some initial data. This is second order in time. So initial data means we have to specify initial values, phi, and the first derivative of the initial values at the initial time. And then the initial data. So tell us about the first time derivative, here the initial data, and the second time derivative, that's the wave equation. But now we can differentiate the wave equation in time, and we can construct all higher time derivatives. Okay? We can basically build a Taylor series, just differentiate this in time, then we differentiate the right-hand side, we commute this, and so we can formally build up a Taylor series for the full solution. We'll just write it down in terms of our initial data. Question is, so this is a formal power series, does it converge? And the answer is yes, for analytic initial data. And this is a famous theorem of Cauchy-Kovalevsky, and we're going to write this down here. These two guys. And so we have, here I've written this down. I'll just go through it very quickly. So you have a general problem of this form. So with m unknowns, they can build up a complicated right-hand side. Here we have assumed that this is second order in time. And so my right-hand side depends on up to first time derivatives, mixed derivatives in time and in space, all the functions, the t's and the x's and so on. But I assume that this function has to be analytic, and my initial data, which I call f and j, they are also analytic. So my initial data are, so the initial phi is f, the initial time derivatives are g, and then there exists some neighborhood O of the initial hypersurface, where I have exactly one analytic solution of the whole PDE system. That's the theorem. Okay, so very nice. It gives me everything that I need. So this shows that the wave equation and also a wide class of similar equations, they have an initial value formulation for analytic initial data. Okay, a very wide class of functions. And then there's a large class of these solutions, basically as many as there are pairs of these analytic functions, f and g. Okay, so that looks like we're done. Okay, this looks very great. Yep. So it's analytic. So there's going to be some convergence radius and so on. But we will not be concerned with this, because what I convince you now is that while this is a very nice theorem, in practice it's pretty useless. Okay? Because analytic functions are not that interesting. They're not that interesting. We have to consider non-analytic functions. Analytic is useless. If you stay in this class, they're kind of useful for many purposes to show that you have a sufficiently large class of solutions. But if you want to do the real physics, you have to go beyond analytic. And so we don't care about the analytic convergence radius, really. Right. So you can't, in practice, you can't treat things actually analytic. So that's what I'm going to explain now. Okay? All right. So I want to make a few points. So one thing, this is a nice example. It's a well-known example in the literature. So if you don't have analytic coefficients, even very simple linear PDEs like this trivial one here, they may not have, in general, they don't have any solutions. Okay? So in general, things are very complicated. But then also, analytic solutions are far not enough. Why? So for analytic solutions, as you know, any finite neighborhood of knowing where the data are, so where you can compute all the derivatives at one point, they determine the whole solution, at least within the convergence radius. So from one point, and all the derivatives, you know the solution, a whole region of the space-time. Okay? But for relativistic theories, this makes absolutely no sense, because information propagates at a finite speed. And so from information just at one point, you can't know everything which goes on in a whole region of the space-time. All right? So analytic is nice, but it's clearly not what you need for theories. You have to go beyond analytic. You have to consider causality. Is very important. So that we can require smooth or CK as you like. For us, we can just make things simple and require smooth functions instead of analytic. And also, this Cauchy-Kovalevsky theorem, it doesn't distinguish. If you would carry this out for the equation, it gives you exactly the same kind of answers. So it doesn't distinguish between, but they have completely different properties. The wave equation is a wave equation that has hyperbolic propagation at a finite speed, and the Laplace equation doesn't have finite propagation speeds. It behaves in a completely different way. So we need more theory to distinguish between these two kinds of physics. There's a very nice example. I just want to flash it, really, not use as much time. It's also well known due to this mathematician Hadamard. You look at both the wave equation here and the Laplace equation, where they just differ by the relative sign. So we do it in one space dimension. They just differ by the relative sign between the time derivatives and the space derivatives. And then we construct some functions that they look very, very similar, which solve the wave equation or the Laplace equation. So the only difference really here is that there's a sign here and a hyperbolic sign there. So we can set at t equals 0, we can set the initial data in this way. And then we find that, so the Cauchy data, they converge to 0 as we take this number n to infinity. For the wave equation, the solutions, so the initial data converge to 0. For the wave equation, then the whole solution converges to 0. But for the Laplace equation, the solution actually blows up for any t which is larger than 0. Okay? So they show completely different behavior. They express very, very different physics. And so there is this key idea of hyperbolic equations. So hyperbolic equations are those which have stable solutions for the initial value problem. Okay? Where as we said yesterday, the solution depends continuously on the initial values, which here it happens for the wave equation, but it doesn't happen for the Laplace equation. So it's a nice example which shows this big difference. Now, if you want to show well-posedness, for example, for the wave equation, you can build this Cauchy-Kovalevsky theorem to give you some intuition, but then you have to use different methods. And so this is not very hard. You can find a derivation, for example, in the Wall book. And I have summarized exactly this derivation here on 3 slides, but I'm not going to go through it. I just have included the slides as lecture notes for completeness. So you can prove posedness within smooth functions is not terribly difficult. It's basically 3 slides, but I don't want to go into it in time on this. So I want to go and look at more interesting things, which is nonlinear partial differential equations. So now let's see what happens if things are more complicated. So nonlinear partial differential equations in general have to be discussed on a spaces. You have a new partial differential equation, you need to analyze this one. However, it turns out there are some subclasses which you can cover by a general theory. And luckily, the usual differential equations that you have in theoretical physics, that most of them, they fall into these nice subclasses where you can have a nice discussion and treat a whole class of solutions at once, a whole class of equations at once. Okay? And so one very important are the quasi-linear equations. So these are linear in the highest derivatives. Also, the part of the highest derivatives in the equations, this is called the part, it can have coefficients which depends on the independent variables and also lower order derivatives. So for example, if you go back to our wave equation here, we have this down. We have this down here. So for example, we have here this will be the part of the wave equation with the metric, and so if this is the principal part, and so if this depends, this can depend on where you are on the solution, the first derivatives, but not, for example, on the second derivatives. All right. And so these quasi-linear PDEs, this is a very important class of equations which does allow statements on well-posedness, and then afterwards on the numerical methods that you can use, simply based on what's the principal part, so how the highest derivative part looks like, and the Einstein equations, if in the standard ways of writing them, in particular, they are quasi-linear, so they fall into this class. All right. And another class is a more special class is generalized wave equations where the GAB is a smooth Lorentz metric, and you form the principal part in exactly basically just by the wave operator, and then you have some right-hand sides which can be more complicated. So this is a bit more special than this more general statement of quasi-linear. And then of the quasi-linear ones, there will be another subclass which is called strongly hyperbolic, and it's the standard classes of hyperbolic equations which give you a well-posed initial value problem. Basically, these two, either a generalized wave equation like generalized harmonic, or something which is called strongly hyperbolic, and we'll see following what that is. So these two are your friends, and if it's not of one of these two classes, then things get very complicated. All right, so let's look at some examples. Let's look at a very simple equation. Let's look at the advection equation. Who doesn't know? Who has never seen the advection equation? You all have seen the advection equation. Excellent. Right, so a correction equation is that, so now in one time derivative plus space derivative, and then here we can have some coefficients here which we call v, because they will afterwards they will turn out to have the role of velocities. So now we have this nice linear equation, and the question is how we write down the general solution. For example, we would like to know the general solution, because once we have written this down, we can take the norm of the solution and then check whether it's well posed. Okay, norm is appropriate. So for that, it would be nice to just write down analytically a general solution. And so we have the idea that, well, since this is linear with constant coefficients, it's actually very fruitful to look at the Fourier transformation. So, and in particular, we'll just need the Fourier transformation in space. So as you know, the formula for the Fourier transformation, you have a choice here. It's the minus I or the plus I. You make this choice, and you know, of course, the magical feature is that the Fourier transformation of a derivative is just algebraic multiplication in Fourier space. Okay, so if you can do this is the absolute magic, which is that the root of all the theorems about the continuum problem and the discrete problem of linear partial differential equations and nonlinear ones, because the nonlinear ones is you linearize them around some point and then you iterate and you show that it converges. So this is really at the root of everything. Okay, and now we're going to exploit that. So if we insert the Fourier transforms into our original equation, then this partial derivative with respect to time is still a partial derivative, but the spatial derivatives, they have now become multiplications with the wave vector k. So these are not partial differential equations anymore. Now these are ordinary differential equations for the Fourier transform. And yesterday we have seen how one solves ordinary differential equations that are linear just by this exponential ansatz, this exponential acting on the initial data. Okay, so this is the big trick. You go to Fourier space, you make your partial differential equation algebraic in the spatial derivatives, and then you can treat it with the methods of ordinary differential equations. Okay, and now in principle you know what to do. All right, the rest is just relatively straightforward things. Now we have the solution in the Fourier space. Now we would like to recover the solution in the original space. So what we do, of course, we just do the inverse Fourier transform. We write it down, all definitions of the inverse Fourier transform, insert this here. And so now we see, so there's this factor e to the I k x minus vt, and transforming my Fourier initial data. And so that just gives me my time-dependent initial data, which depend now on x minus vt. Which tells me that basically the general solution of this equation is just I have my initial profile, and then this initial profile is just, as we say, advected, just moving without change with the velocity v. That's the physical interpretation of this equation. Okay? All right. As we'll see afterwards, essentially, as far as the principal part is concerned, all the other equations are in some sense combinations of advection equations, really. The wave equation is just, in fact, two advection equations. All right? Okay, we'll see this afterwards. So this Fourier method works for general constant coefficient PDEs. Okay, if the coefficients depend also on x, then things become more complicated. Because of this, so we can evaluate the norm now, and obviously the norm is the same as the initial norm, so obviously the equation is well posed. So this is this big idea which I've stressed, that you can solve constant coefficient equations explicitly. You don't have to carry this out, but now in principle you could use the same method to check well posedness for any other equation that you have. If it's linear constant coefficient, and just check how it works with exactly the same methods. All right. Now this was one equation. Now we go to systems. So let's take. So now it's going to get ugly because now we get all kinds of indices and matrices and so on. But since we already have a solid understanding of kind of what's going on so far, we shouldn't get confused by all these extra indices. So a first-order differential system, we have now the U is a vector, has an index A, whatever the physical meaning of A is, in whatever space it happens. A time derivative of this is derivatives, dj, acting on, this is the spatial derivatives, acting on my variable, and now this gets multiplied with some matrix. So this is V, the V is just for one dimension. Now the V's get extended to a whole matrix. Same procedure as before. I just go to Fourier space, then the derivatives disappear. I get the spatial derivatives become algebraic in Fourier space. I know how to solve this explicitly. It gets all more lengthy, and sorry, possibly I mixed up some indices. You can check that, but it follows exactly the scheme as before. For some of the analysis, it's going to be useful now to choose a particular direction in space. Let's call this n. N is a unit normal vector. And so with a unit normal vector, you can project out a particular direction of this matrix, and then the k is not a vector anymore, but it's just a number, it's the absolute value. This makes things a little bit simpler. Now we use exactly the same formula that we have written yesterday. Now we see why we had introduced k here, and why we have used the complex unit I, because we need it now. We can do the same analysis, and we can split the matrix A in a diagonalizable and an nilpotent part, and we can write our matrix exponential like this. And so we see that if we write like this, and the D if A is diagonalizable, so it's only the D, and the eigenvalues are real, then each component of the solution U is in the diagonal basis is vector just with the speed which corresponds to the eigenvalues. And we can define something which is called characteristic variables, which is p times u. Now I will write this on the blackboard. Let's see if I can manage this very early time. So let's write very schematically our equations. So we had dt u is au. All right, now just to simplify the notation, I just write it with matrix notation, and now there is this p, which is supposed to be the similarity transformation to make it diagonal. So let's multiply with the p from the left. Why not? All right. So but the p is all constant coefficient. P is a constant coefficient matrix, so we can draw this in here. All right. Now you know what's coming. Now comes like theoretical physics trick number 1. Right, and so we write here p minus 1p. All right, standard trick. And so now what we have here, now we have dt pu is pa, p minus 1 is d acting on pu. So these transformed variables, pu, these are the ones where this matrix has now become diagonal. Okay, so for each component of right, for each component of this thing, let's call this now, I don't know, u prime. Okay, so the new equations, they look like, dt u prime, 1, like the first component. This is equal to, this is diagonal d1 1, u prime 1, and so on, blah 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 blah. So now for each of these variables, the primed variables, we have an advection equation, and the d component is its advection velocity. Okay, so these new variables after the similarity transformation, these are exactly the variables which are advected, which are moving with a constant speed, which is given by this matrix element. All right, so initially you have the initial differential equation, and have some complicated behaviors and very complicated physics, but once you get to these new variables, pu, which are called the characteristic variables, each variable moves with a fixed speed. Very, very simple. Very simple geometric interpretation. All right? Okay. So what we see is that, so if this term isn't there, if it's diagonalizable and we have real eigenvalues, the norm is preserved. The characteristic variables built like this, they have a very simple interpretation, and the whole problem is well posed. If you make your equation more complicated, let's say this is a more complicated one, so placing the indices, so now we have some lower order terms, you can get some nasty features. For example, you could get some exponential growth. Why can you get exponential growth? Yeah, we see, for example, this term here, like if imagine this is actually small and this is dominating, you get ut is bu. If b is positive, you get exponential growth. So this have nasty behavior. As we have said yesterday, exponential behavior is perfectly fine with well-posedness. So having some lower order terms doesn't change the principal features. It just creates some possibly inconvenient growth. Okay, so now, right. So now what happens otherwise? So now, for example, here we have some other matrix. In fact, comes from the Einstein equations. We computed its Jordan form. So this one, in fact, Jordan form is a mathematical command. You can just do this. You can bring any matrix into its Jordan normal form. And so we see now here, this is not diagonal. This has some off-diagonal pieces. The off-diagonal pieces correspond to this. Okay? If you have these off-diagonal pieces, they will, in the second part of the equation, they will create some polynomial, which depends on your norm, you will find that this violates the well-posedness. Your norm will grow uncontrollably. Okay? This would be the case where the eigenvalues of D are real. In fact, they're all here -1 or +1, but the n is not 0, and you have these extra terms which destroy well-posedness. But you can have something even worse. You could have complex eigenvalues. Then you get exponential growth right here, and then this is also not well posed. That is even worse than this. Okay? This would be, for example, if you take an elliptic equation and you try to treat it as an initial value problem. That doesn't work at all. This is like even worse. Yeah.
Why do you have to choose the reaction n?
I introduced this because I'm gonna need it like on the next slide. So for the moment, I'm sorry. For the moment, it doesn't seem to be that important, but on the next 1 or 2 slides, I'll have to say something about it. Okay. Well, obviously not on the next slide, maybe on the one after this. Yeah.
Can you go back to the slide?
Yep.
You were saying that complex eigenvalues give the exponential growth, okay, and it's not well posed anymore. But isn't the quasi-normal problem complex eigenvalue problem? Isn't the problem of quasi-normal well posed?
No, but here we talk in the context of evolution equations, of eigenvalues of this matrix of the principal part. So this is a different part of eigenfrequencies and so on. Yeah? It shares some math, but it's in a completely different context. All right. So now we can make, now that we have seen this, we can make a nice classification which entirely relies, just to explain this, just flash this again, right? So all these statements about well-posedness, really, they all rely on the linear algebra properties of this matrix. Is it diagonalizable? Are the eigenvalues real? Are they not real? Very simple properties which we can check just on this matrix of the principal part. Okay? And so now, based on the classification that we have derived here, discussed, we can now classify hyperbolic systems in the following way. So that the weakest form, somehow, in terms of usefulness, is weakly hyperbolic. So here, the speeds, which means the eigenvalues of A, they're all real. But you can have, but it's not diagonalizable. So you can have this part N, which destroys the well-posedness. This means that in some appropriate, like fine-tuned sense, you can still make it well posed, but not in any practical ones. As soon as you would add low-order terms, this gets destroyed. So for all practical purposes, weakly hyperbolic means it doesn't have a physically sensible, well-posed initial value problem. Okay? This equation, you want to solve it. If it turns out it's weakly hyperbolic, you can forget about it. Next case is strongly hyperbolic. So it's weakly hyperbolic with a complete set of eigenvectors, or basically your characteristic variables that span the whole solution space. And in this case, you can check that this is equivalent with having this other part n being 0. So this is now completely diagonal. Okay? And so these ones have a well-posed initial value problem, exactly what we said before. If the D is diagonalizable, yeah. Sorry, I don't know. This is right. You have to. So the question was whether certain quantities have to be bounded. It's true. So there are some technical things that I'm glossing over now. That. You have to make sure that all the operations, for example, when you make the similarity transformation, that is actually regular. Okay, if this would be in some sense singular, this would be consistent with what I've written down here, but we don't want that. So that if you want to spell it out properly, you have to make some extra conditions that certain things have to be regular. That is correct. So there's a number of technical details which I have to sweep under the carpet. Okay, but it's kind of, if things become singular, then it may formally satisfy what I've said here, but it doesn't actually work. Okay? All right. All right. So strongly hyperbolic is fine. But now comes in what was this other question that we have chosen a particular direction. Okay? So if basically you choose a direction, because this A had actually 3 indices. So A wasn't really a matrix, it had 3 indices. So that's why we chose a particular direction that we're projecting out one direction, so it's a matrix with 2 indices, and then we you can have the fact that basically depending on your direction, the mathematical properties are changing. Okay? And that's the difference between strongly hyperbolic and symmetric or symmetrizable hyperbolic. This is basically strongly hyperbolic, but you can do the same similarity transformation in all directions. You can diagonalize it in all the space directions at the same time, which in this one you can't do. This one gives you even nicer features. You have a conserved energy. You have some nicer properties with the boundary conditions, but you don't need this just for well-posedness. And then the one which is strictly hyperbolic, which has all eigenvalues distinct, but it's not going to be important for our purposes. Is kind of clear? All right. This is all a bit lengthy and complicated, but the important home message is that there is this very few nice basic tricks, Fourier transformation, some linear algebra, and then you can classify, based on the linear algebra properties, you can classify large systems of equations, and you just look at the principal part, and you basically know what the mathematical properties are. Okay, so it makes it very, very efficient to treat. Okay, let's see. So now we have some more remarks. So quasi-linear, so basically that means you can have non-linearities, but they're only in the lower terms, so that's in particular the case for the Einstein equations. Also, so if you now have such nonlinear equations, then because the nonlinearities are only in the lower order terms, all the well-posedness that carries over from the linearized solution to the full nonlinear one, and unless these nonlinearities become somehow singular. If things become singular, you have to be more careful, but as long as things don't become singular, this is fine. I think I don't want to really talk about the existence problem. Now, one question that can arise and has confused people in relativity in particular for a long time is that having things first order in time was very convenient and in our analysis quite essential for the whole solution procedure in the Fourier domain. But what happens if you actually have higher differential order systems? So for example, the wave equation is actually second in time. Now what do you do? And we'll get back to this. So a little bit, so a pre-remark about the history in general relativity. So if you have first order systems, what first order systems we have in physics? So for example, fluid dynamics, which will be talked about. That's first order. That's a first order system. Or the Maxwell equations written in E and B. That's first order. And so this theory applies directly to these kind of equations. But the Einstein equations, they're second order in space and time. They don't immediately fit into this scheme. And in fact, it took until basically mid-2000s to clarify in which sense the Einstein equations are well posed for like general formulations. For the formulation, I said it was done in the 50s, but just for this special harmonic formulation, and the reasons why harmonic doesn't always work. For other ones, this was basically done 50 years later. And I'll say a little bit about the insights which have been gained and that are available now for more general formulations of the Einstein equations. Now, let's talk a little bit about the wave equation. And again, let's make it simple. Let's talk about just the wave equation just in 1D. So we start in the second order form, very simple. So c is the propagation speed of our equation. And now we can write this in all kinds of different ways. So for example, we could write as a mixed first and second order form. So we introduce one new variable, which is pi, and then we have one equation for phi dot and one equation for pi dot. So this is now second order in space. So this seems pretty convenient because now it's first order in time. So regarding the time evolution, it's like we've said yesterday, ODEs usually want them to write first order in time. So that seems to be convenient. But we didn't do anything to the derivatives. But you can go further and you can write it in the complete form that we have just discussed. But then you have to introduce more variables. So for example, to reduce the second derivative here, you introduce a new one. Let's call it psi. Psi is phi, the x derivative. And then you have these two definitions, plus you have now a time evolution equation for phi, and one for pi, and one for psi. So the system of equations gets longer and longer. Okay? And then also now you have added new constraints. New equations which are not evolution equations, which don't have time derivatives, which have to be treated as constraints, like this one here. Derivative of phi is psi. This you can easily check that this constraint is preserved by the continuum equations. But if you discretize this, and maybe you add some nonlinear source terms, who knows how well this extra constraint is going to be preserved in the time evolution. All right? So now we see that we can write this simple equation in many different ways, but we have to be careful. There might be some trade-offs, whether one works better than the other one. Okay? And we see that, for example, the one that fits with the theory which we had developed before, the first order one, it's a lot more complicated. It has extra constraints about extra instabilities and so on. All right. We can also see here so that the evolution equation for phi, in fact, decouples. That makes it a bit simpler because on the right-hand sides, there is no phi. So we can solve for the pi and the psi because these are coupled together. And then once we know those answers, then we can integrate up the phi afterwards. Okay, so the phi we don't need the phi to construct psi and pi. If we write just this main evolution system for pi and psi in the form that we had before, we can write like this, where now U is a two-component vector, pi and psi. Then in order to get the equation from before, we will get this matrix A. Very simple. It has eigenvalues plus and minus C with these eigenvectors. Then according to our recipe from before, we can compute what the characteristic variables are. Let's call them U plus minus, and they are psi plus minus pi. These are the equations that it satisfy. And so now, from our interpretation from before, new variables, variable travels to the left, one variable travels to the right. A very simple behavior. If you do the exercise with the wave equation, so you will code up exactly this. You will code it up. You think, the solution that's a bit strange. Maybe it's not correct. How can I find out if it's really correct? Well, one thing we test, but another is to plot not your phi and pi and psi, but to plot your characteristics, because you know the behavior they have, that they have to move speed to one side or the other side. Check whether this behavior is correct. All right? And another important will be to compute the energy of the wave and check whether the energy of the wave is. Okay. And then it's also very easy to see that the solution again preserves the norm, so it's opposed as it should be, because this has nice, it's diagonalizable and it has nice eigenvectors. Okay. So let's look at another example. So wave equation works. We're not very surprised the equation works. Let's look at another example. This is a nice system of two coupled equations. Maybe you have your new, you devised your new Lagrangian, your new very simple theory of everything. You have your Lagrangian, you derive the equations, you get this, you're very happy with this. It does not my new very simple theory of the universe. Now you crank it through this theory which we've have developed, and you find it. So you write in this form, and this is your matrix. It's not diagonalizable, and so in the classification it says no, it's weakly hyperbolic, not well posed. You say, well, I don't care about all the theory. I'm going to evolve it anyway. Okay, let's just code it. Let's evolve it. Well, you can actually derive an explicit solution with a fixed frequency. This is the explicit solution. You can check this by yourself. And then you compute, for example, the L2 norm of the time-dependent solution divided by the initial data, and you find that this norm grows linearly, but depending on the frequency. So, for example, if you quantize this, the finer you grid this, the higher frequencies you get, and the stronger it grows. So this is not well posed. This doesn't have initial value problem, and this doesn't. So your theory be disproved. This can't be a meaningful theory of something. Okay. All right. And then the ADM equations. So let's look at the Einstein equations that we have seen yesterday in the simple form with the metric and the extrinsic curvature. But let's make it a little bit simpler. The equations were quite long. First, so we have to introduce some gauge condition. This is a simple one, that the lapse is the determinant of the 3 metric, the square root. You could use another lapse condition. It doesn't really matter. You could make it 1. Okay? But now we just do it one space dimension. So we just consider like a plane wave, let's say traveling in the x direction. We linearize it around flat space. So now your Einstein equations, they look really, really simple. The same 4, compute our Jordan normal form, blah, 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 that's what it is, and we see it's not diagonalizable, and so this is only going to be, okay, and indeed, if you have your numerical solutions, they will not converge, and they will show all kinds of strange features, okay? It turns out that, for example, if you dimensional problem, which is, it works fine, and this is because here you can have plane gravitational waves, and degree of freedom, which gives you trouble here, just doesn't exist. Okay, and so this was a big historical problem in numerical relativity, because what people did was they coded up these ADM equations. They found that in 3 dimensions, this is expensive anyway for the computers they had. So let's go back to spherical symmetry. In spherical symmetry, this worked great. Then they had bigger computers. Then they tried it, let's say, in axial symmetry. And then the whole thing didn't work and had all kinds of instabilities. And it took them a few, basically decades to figure out why. Well, because while for spherical symmetry you would get well-posed equations, for if you don't have spherical symmetry, you get weakly hyperbolic equations that don't have well-posed initial value problems. So that doesn't work. Okay. All right. Now you can say, well, there's a catch here, because while the ADM equations are first order in time, they're actually second order in space. And the theory from before was first order in space. So what should I do about this? Okay? And then there was a long war. Usually I refer to this as the hyperbolicity wars. Most of the war was fought, in fact, at AI. Where's Jan? Yeah. Discussion, took many big ugly fight. Basically, there were 2 opinions. What should we do? Well, one opinion was, of the mathematicians, the opinion was that since this doesn't fit to the nice theory that we developed before, we shouldn't do this. We should just make it first order in space and have these extra constraints and extra variables and just live with it. And the other, maybe we have to develop a theory which describes this kind of systems. While the particular ADM one doesn't work, maybe there are other systems that have, but they're just fine. We just have to develop the theory. And the second strategy that worked, and this is what most people do right now, and this is what I'll describe a little bit afterwards. Okay. I think I skipped this. You can look at the slide. So there's nothing more very substantial. I've written down for you what actually the scalar field energy is, and this is mostly for reference. If you want to write the wave equation code, and you want to evaluate the energy to check how well this is preserved, then you have it here. And you have to talk about boundary conditions. Okay. So now we just pretended that there are no boundaries, that it was what's very usual if you talk about all kinds of aspects of general relativity. You say, let's first have a manifold without boundaries. And that's very simple. It turns out that if you have boundaries, things get a bit nasty. So what about imposing boundary conditions? If you have a finite grid without boundaries, so a simple thing we can do is simply use periodic boundary conditions. So just identify the 2 endpoints. Nice, and you're done. There are no boundaries. Locally, there's no point, which is like a real boundary. Theory from before applies just fine. And if you code up the wave equation, that's probably the first thing that you want to do. It's very simple. Of course, it's not that physical. For example, for wave propagation problems, if you want to solve black holes, but periodic boundary conditions are not welcome. So if you have a finite grid with boundaries, you have to impose some boundary conditions. Typical ones are boundary conditions, or maybe outgoing boundary conditions, that the waves are just going out of the grid. And the way that you impose boundary conditions is that you have to impose them on your characteristic variables. Okay? So now we have seen before, and if you write your equations with the characteristic variable, that one characteristic variable goes this way, another one goes the other way. On your boundary, you would have an outgoing variable and an ingoing variable. And so how do you impose boundary conditions? You can't impose boundary conditions on the information which is going out, but you can put conditions on the information which is going in. So for example, you could reflecting boundary conditions would say what is coming in is the same as what's going out. So a wave which is going to the boundary will be reflected. And an outgoing boundary will be that nothing's coming. So you will simply set the incoming characteristic. The 2 simple things that you can do, and then there's some variations on this, but that's basically it. Now in relativity, most interested in some sense is basically an infinite grid, where things go all the way to null infinity, and then things will become a bit more complicated. But this is an old slide, so it's not tomorrow. I'll just skip that, okay? For the exercises, we'll just you can think of, okay, we just stay with a finite grid, and if the grid is too far in, then we'll just move it further out, and for our current purposes, this is enough. Okay. Now, all right, so today yesterday I was really happy with my timing. Today is terrible, but so is it. Now I want to briefly mention a variation of the wave equation. So once you have solved the normal wave equation, your exercises, you can step it up a little bit, and you can make your coordinates move around the grid. Why would you consider to do this? Well, I think it's what was in the questions yesterday. Remember that we said if you have on a horizon, which is, let's think there's a whole Penrose diagram maybe around this. If you have an event horizon, which is an outgoing null surface, you would basically like to have that your horizon is like a sphere of coordinates. There's like doesn't. Okay, so this shift vector which steers your coordinates, you would have to move it in this direction. Basically, you have to, if the horizon isn't supposed to grow in coordinate size, so it's going to look like a cylinder, like this, x and t. That means effectively there would be a grid point on the horizon which just stays on the horizon. Okay, so you have to move your grid points along this outgoing null surface with your shift vector, and this means that your grid points have to move at the speed of light. A simple exercise, what you have to do is let's take generalized harmonic, a generalized wave equation. Let's forget all about the complicated source terms, but let's just solve the wave equation, but let's solve it in coordinates where the coordinates are moving, maybe with the speed of light or even faster. And then let's see how your numerical scheme handles this if your grid points are moving around with the speed of light. If you can handle this, then you're ready to handle black holes and horizons. And it turns out it's not so hard. Okay, so if you move around your coordinates, you just make a coordinate transformation. You move your coordinate with a speed beta. You can compute what your metric is in the new coordinates. You can compute what your wave operator is in the new coordinates. We're not going to do all the calculations. You can write your wave equation now in terms of these, explicitly in terms of the beta, just writing this out. You get something which is this looks nasty, this looks kind of longish. But look at this, for example, here you say d by dt of something which is your minus phi dot plus phi, plus beta phi prime. So maybe we just introduce a new variable, right? For the normal wave equation, we had this new variable pi is phi dot. So now let's take this extra term, and with these new variables, actually doesn't look so bad. Okay, so these are new evolution variables. And so now your beta is 1, things are moving with the speed of light. So the interesting exercise is to solve these equations. You start with beta equals 0, the normal wave equation, you make beta larger and larger, and you see what happens. And you're quite close to the kind of phenomena that you see in numerical relativity if you treat horizons. Okay, I think I just put this for reference to explicitly say what the A is and so on. I don't think we want to discuss this now. And the same thing for boundary conditions. I gave you the basic story before, how to set boundary conditions. So here this is just written out explicitly in the kind of variables they have for the wave equation. I want to show you this. So now we know to treat. So now let's go to some more interesting equations, which are real gravity. And so the simplest thing is just let's take spherical symmetry, zero shift vectors, a very simple spherically symmetric metric, and then let's put the of this, but let's gravitational field. So now this is already physically interesting. So for example, you could have a scalar field that is self-gravitating and is collapsing under its own weight and forms a black hole. All this is included in these equations. And so here the equations are written out. This is the Einstein equations for this metric, and these are the scalar field equations. So this is basically the wave equation, the scalar field coupled to gravity. These are very simple equations. Once you have coded up your wave equation, it's quite feasible to code up these ones, and off you collapsing scalar field into black holes. All right, let's look a little bit at the structure of these equations because it's quite interesting. So here, this is the part of the wave equation. It looks like it looked before, but of course for flat space we have alpha and a equals 1, and so now these metric coefficients come in everywhere, but it doesn't change a whole lot. But now we also have equations for the metric coefficients. So what we have here, this is a spatial derivative, spatial derivative, spatial derivative. So these are actually constraints because they don't have time derivatives, and this is a time evolution equation. Now you have a choice whether you construct A from the time evolution equation or from this constraint. And the usual way is you eliminate, you eliminate this one, and so all the dynamics, all the time derivatives are in the matter, and the spatial derivative, so all the metric equations all have the spatial derivatives. All spatial derivatives. It's a very, very simple form. It's very easy to code up, and you can just do this and have a lot of fun when you're collapsing black holes and forming singularities and all kinds of fun stuff. Okay, now, all right. So this is the last of this part. One thing, so I skipped many technical details, but there's one thing that's very important. Is the whole theory of how you do things depends a lot on whether you have smooth solutions or distributional solutions. If you have something like the wave equation, if you have smooth initial data, then you will have smooth solutions later. But if you have nonlinear equations, like this is a very popular simple example, it's called Burger's equation. It's basically here the characteristic speed depends on the solution itself. In this case, so now the characteristic speeds, they depend on the solution, and then you can have all kind of strange phenomena like here, where for example the peak of the wave, they overtake the rest of the wave. Like water waves, like tipping over. Okay? So this and if you have standard hydrodynamics, you will hear about this week, but then about numerics you will hear from Luis next week. The whole theory of how you treat these equations, how you solve them numerically, is very, very different from how you treat the wave equation. Because in this case, you can start with smooth initial data, but after some time, they become singular, they become distributional. In the context of fluid dynamics, this is known as shocks. So you have a complicated fluid. Oops. Right. After some time, you get shocks. And a lot of the effort in gravitational hydrodynamics is how do you treat these shocks? How you follow them? How you treat them properly? And if you have generalized wave equations, you don't smooth, like in the Einstein equations. If you have the Einstein without any matter, the only non-smoothness that you can get is if you choose bad coordinate conditions, or if things become singular, if you form a space-time singularity. And how to do singularities, we'll talk about tomorrow. Okay, fine. So this is really all you need to know about the continuum problem for smooth solutions. And now we're going to talk about the numerics. There are many different methods, but the only one that I'll talk about in detail is finite differences, and how to make finite difference schemes stable and avoid that they get unstable. All right. Now, so I think that's, I'm not going to finish this now, but let's see how far we get, and then I'm going to finish this part tomorrow. So so now before we start, we have to do some preliminaries, and so we have to talk a little bit about how we're going to read up the data. Let's keep it simple But let's make it an equispaced grid. All right, so that seems the simplest thing to do. So consider an equispaced grid. Let's say d dimensions, but in practice we'll do 1 dimension. Then you have to you want to define a few things, like for example inner products between your functions, and we had the definition of stability. We had it yesterday. So the norm of the solution at time step n is bounded by the initial data. This is just repeating what we had. And so now we can, for example, we can consider waves in this grid of different frequencies. So here we have waves, there's a smaller frequency, higher and higher frequencies, and clearly there's a maximum frequency which you can represent in your grid. Right? This wave is well resolved. This not so much, and here it's just jumping up and down. So now which waves can we represent on this grid? So with this kind of feature, so we have we call our circular frequency omega, and then we have omega goes from minus, so n is the total number of points. We have these many frequencies. Usually we'll introduce another variable we call psi, which is the standard frequency omega, rescaled by the grid spacing delta x, which now we call it h, which is a standard kind of naming. And so if you check now this psi, this goes exactly from minus pi to pi. So the absolute value pi is basically the highest frequency you can represent on your grid, and this can go in the negative, travel in the negative direction, or travel in the positive direction. And so now we've seen before in the continuum problem that it's very useful to use Fourier transforms, and the same thing is true in the discrete problem. So now we can, for a grid function Vnj, so this is some value v at spatial grid point j, and at time step n, we can just represent this as a sum over some plane wave terms into I omega x, with some amplitude v hat, and the v hat amplitude, which depends on the frequency, is basically your discrete Fourier transform. So it's very useful to describe your grid, your functions in space and time as Fourier amplitudes which depend on the frequency. So in order to use the same kind of methods which we had before from the continuum problem, all the benefits that we have in Fourier transforms, we want to use them also in the discrete case. All right. Now, so one thing that we already see, which is going to be important later. So when can you expect that you will get an accurate numerical solution to your problem? Well, you can only expect this when your signal is valid, basically when frequencies of minus pi or pi. All right. So this was just some basics about how we manage grids. Equispaced grid, introducing these frequencies and seeing that frequencies, they go from some minus maximum value, positive maximum value. All right, now we want to discretize, and so we need some finite difference formulas. And so now we'll check how do you derive a finite difference formula, a finite difference stencil. You can do this approximating your solution with a polynomial. Let's walk through a simple example. Is it out of battery, or is it just? All right. So before it was fine. I can swallow it. Right? Let's see if it's this way. It's too close. Maybe you see it better. You see this better. I see. Excellent. All right. let's do some kind of Taylor expansion now to second order. So this is our functions f on x, very simple. We have three coefficients, a0, a1, and a2. So in order to determine them, we need 3 grid points to define their values. Let's make them equispaced. And so let's make our grid minus h, minus delta x, 0, and h. And see what equations we get. So now we say that, so f of minus h is f1, and f of 0 is f2, and f of h is f3. And now we solve. With this input, we solve for the coefficients are, and we find some formulas for the 3 coefficients. And now we can take a derivative of this formula with these ansatz. So for example, dxf is now f3 minus f1 divided by 2h. And we can do the second derivative, and we get a similar formula. Okay, so now under the approximation that our function is given by this, so that just we take the first 3 terms in the Taylor series and neglect the next term, we get these discrete formulas for our derivatives. So this is a finite difference formula or finite difference stencil. Okay. We can also, since we said that Fourier transformations are very useful, you can also carry this over to the Fourier, just to outline how this works. So now if my solution f of x Fourier domain. We can see this is actually interesting because, so if I take the limit now to the continuum, my delta x, my h goes to 0, you see that then I have just I times omega. This is the true correct formula for taking the derivative in the Fourier domain, just multiply with I times the frequency. Formula is different. So this is my error. I've taken more terms in the Taylor expansion, just take this order, which I get from here, and so I see at higher frequencies I don't exactly have the correct result. Just at low frequencies is correct, but at higher frequencies I have some deviation. All right. So now that I've shown you how to derive a finite difference stencil by yourself, I have to tell you that in fact there's a very simple formula how to do it in general, and in fact, so this is due to this guy. You see that this was found quite late. So if this is as a one-liner in Mathematica, so this gives you basically any finite difference stencil that you want. This is very nice. And if you have non-equispaced gradient, but you can go to this, which is this. You can. There's a very nice. Mathematica has a very nice and simple practical tutorial, and then you can go to this website to type in which grid points you want to use, and they don't have to be equispaced, and it gives you your finite difference stencil. Derive it with a Taylor. This is something which is very useful to know, if in particular if you go to non-equispaced grids and more complicated higher order formulas. So this is very useful to know. Okay. So now with all of this, let's look at some example now. So let's go back to our favorite example, the wave equation, and let's discretize the wave equation. All right. So this is the wave equation. Let's say our grid is x goes from time. We have some things. I don't see where the flat part is.
Yeah. You can see. This should be better.
All right. Is this better? Yeah. Kind of. All right. So then I have my initial conditions. This is how I grid up my space. So this is the x direction. We have points j minus 1, j plus 1. Then this is my time steps. And now let's do a simple stencil. Let's say I want to compute. I want to just look at the next neighbors. So let's look at these points. Let's see what derivatives I get the formula I get if I just use these points. And now, for example, I use my second order finite difference stencil from before, and then I can, for example, the second time derivative, I write it, I get this formula. So for the second time derivative, I use n plus 1, n and n minus 1, so these 3 points. And so, for example, I can use this, for example, to compute the derivative here, using the value here and the value there. And the order is delta t squared. And I can do the same thing for my spatial derivative, the same formula. I can write this as putting to the left the value of my solution at n plus 1 and spatial grid point j, everything else on the right. I've introduced this nice factor lambda, which is just delta t by delta x to simplify my equations. And this is my finite difference scheme. Okay, this is very nice, very simple, and it's actually called frog. Very popular. All right? Now I want to know, now I can just run this, but now I want to know whether this is actually going to be stable. You can just try it out. Try, time step half, 1, 5, and you will find out if the time step is small, this works perfectly well, but if the time step is too large, it doesn't work. Which shouldn't be surprising, because yesterday we have done this analysis for the Euler equation, just for simple ODE, and we found out if the time step is small, it works, and if the time step is large, it doesn't work. So it wouldn't be surprising if for a PDE, we get something which is very different. All right, so how can we analyze this? Well, let's write again our solution as a superposition of this kind of Fourier mode. Let's just pick one mode. For example, let's see how the scheme acts on a single mode. And then u at time step n is basically and so the final solution is just n updates, q to the n times your initial solution. Okay? So, and the norm of this is called your amplification factor. So, then basically your step is smaller than 1 is decreasing every step. Use the energy, you're going to gain energy. You can say, well, the best thing is I have it exactly at 1. But if you have exactly at, you say, if you to q is a little bit larger than 1, to slightly decrease a bit of energy, but at least you're exploding. So basically, so what you have to check is if your q is too large, larger than 1, and then it will be unstable. And q equals 1 will be. All right. Was by delta x, and then you have basically for psi between minus pi and pi, for the lambda that you have chosen, for the delta t divided by delta x that you have chosen, this q doesn't get larger than 1, and you have to discuss this quadratic equation. And I'll tell you whether for a given lambda your scheme is going to be stable or it's going to be unstable. Now, so I don't want to go into the plots. All right, so maybe let's take one more thing and I'll just finish this argument. There is, to this whole analysis that a difference scheme, you check what's the amplification factor. There's a interpretation, and this is the following. Whatever this then the points which I've drawn, this is your numerical domain of dependence. analogous to the domain of dependence, which we okay. And so now, but now the question is, what's the propagation speed? You know, the characteristic speeds in your equation. That the continuum domain of dependence is larger than your numerical domain of dependence, and here is smaller. And it turns out that this one is stable and this is unstable. And the geometric interpretation is that the numerical domain of dependence, like in this plot. It doesn't include, there's physical information which comes from outside the grid, which is not taken into account at this point. And then you can have inconsistencies, and these inconsistencies can build up in an iterative scheme, and then it's going to be unstable. So essentially, you will get that what you get from a discussion of an equation like this, like what's the allowed time step, we'll get something which is consistent with this picture, at least in one space dimension, where it's just very simple to draw, that the maximum time step that you can do is just given by this condition, so that the physical domain of dependence is included smaller than the numerical domain of dependence. All right. Now, okay, so now I will stop. There's just a few slides. We'll do them more. Questions? This was by far the hardest part. Okay, for now it's gonna relax again. So this was a lot of equations, a lot of long arguments. From now on, it's gonna get.
So if you don't ask questions, anyway, stay here because we are taking another shot of the conference picture, because apparently the first shot has some ugly holes. But questions now. Okay, so we.
I didn't see when we use the definition of the vector n at the beginning of the slices. You say that we will see in the next slices, but I didn't find it.
So this was I made this brief remark when I talked about symmetric hyperbolic and strongly hyperbolic.
Mm-hmm.
I said, well, so now the question is whether it's diagonalized, whether this matrix is diagonalizable. Okay? But then the point is, so this A that we had, it wasn't a matrix, it was actually a 3-index object, because there was one index was for the spatial dimension.
Mm-hmm.
Okay? And so in order to really apply this whole eigenvector argument, you have to get rid of the third index. And so you project it out so you choose one dimension. There was something like A, B, whatever, J, wherever the index was, and then your wave vector J. So you assume this goes in a particular dimension, then you project out this dimension, and you have a matrix left over, and then you discuss the eigenvalues of this matrix. Okay? And then you say, can I find this similarity transformation P such that it's diagonal and so on. And the important technical distinction is whether you can find a P so that it's diagonal all the dimensions, or just one dimension at a time. If it's just one dimension at a time, this is sufficient for well-posedness. It's called strongly hyperbolic. And if you can find it such that it treats all the dimensions at the same time, then it's called symmetric hyperbolic, and it's a bit stronger. It has some nice properties that go beyond just being well-posed.
Okay.
Okay, so please come all down. I mean, fill all the front rows, and then go on with the other ones to take another picture.